Talk a bit about frequency response, particularly what would happen for a linear system, and really with a focus looking at this towards sort of a discrete time system first. But let's sort of think about what do we mean by frequency response. At a very simple level, what we're saying is I want to start with a single frequency as an input, maybe a sine wave, and realizing if I go through a linear system, I know that the output will be the sine wave at the same frequency because it's basically an eigenfunction of that linear system. And what I'm looking at then is that I'm going to get some change in magnitude and phase. And that might be talked about as a transfer function h, and we can kind of look at this. So same frequency and only one frequency, but different magnitude and phase, perfectly reasonable. And we want to know what that magnitude and phase is for a given frequency, but more so, I'd like to know what it is for a whole range of frequencies, so I can begin to understand what the overall behavior of the system is in a way that says, okay, what happens for lower frequencies, higher frequencies? Maybe this is a way to talk about filters and so forth. So we could imagine talking about this for a discrete time filter. And again, now these are going to be omega hat because they're going to be sitting in sort of a sampled space. So you could imagine I could have it as being sine omega hat n, or I actually take the complex exponential. Certainly for the omega hat n, I know I'm going to get a real valued out, which is then going to have a magnitude and phase shift. And otherwise, everything else looks just fine. And that's going to be omega times n. Brackets may not be all that necessary. It doesn't really hurt you here, but they're not all that necessary here. Or I can have the exponential form of this. And then when I do that, I'm going to then go, well, there's going to be some exponential shift all the way through this that I'm going to get as a result of that sort of full convolution. You think, that's interesting. I wonder what that actually looks like. Well, if I take this sort of convolution structure, what do I get when I sort of push through this structure? Well, I'm going to get now my y of n is going to be some exponent, going to be something here with all those coefficients with the exponentials in it, and those values of x, and that, again, notice that value of x has been in there and now it's shifted. Well, let me take all those values of x and pull them out to the outside because they're all the same. And now I've got a summation here that has those values plus what looks like values at sort of delays, right? E to the minus omega hat k of all the different k's. Well, this is my x of n, which was actually meant to be that sort of sinusoidal signal. And you're like, okay, that's cool, which is now e to the j omega n. You're like, great, and I've got this extra term here now, which is really based on what were all the coefficients, b of n, which you might imagine is effectively your, impulse response of this. And so there's a way of kind of taking that impulse response with exponential terms in there and go, that works. And if you're sitting there thinking about, wait, is that related to the z transform of this where it's, z minus 1 and I just replace this for z, that also works. Okay, if you're familiar with z transforms at this stage. And so, but what it means is this gives us a definition of what is the transfer function for frequency, both in terms of its magnitude and phase. In fact, it's sort of the arbitrary sort of complex structure there. Now remember that this, because it's discrete, it's going to be pretty much omegas between minus pi and pi, and there's sort of a rotation through that. So that's kind of the range at which you're going to want to look at your frequency response. Because what you realize is outside of that, and we're going to plot one of these, outside of that pi, minus pi to pi, it's going to repeat because it's identically the same. And so just be aware of that normally we're going to kind of focus in this space. So just imagine I have a particular transfer function 1, 2, and 1, very simple FIR filter of 3 coefficients. That would actually mean that my h of j omega would just end up being 1 plus 2 plus 1. But now I get the second frequency and the first frequency. Great! So now I take all of this and I can pull e to the j omega outside here. Well, if there's a 1, that's going to give me one of them. Gives me a 2, gives me e to the minus j omega. So I get this, all of the j omega term here, and this is a very particular property of FIR filters, of these kinds of structures where it's sort of just feed forward and the delays. that I'll pretty much always be able to pull something out of there, and then I have a whole bunch of additional terms. In this case, I can bring the 2 down, and then these two give me a cosine omega with a little bit of small realizing. That's actually then 4 cosine squared omega over 2 times e to this j to the minus j times omega hat. And you think, that if I take the magnitude of this quantity, well, this is just always going to be 1. And the magnitude of two products, if you're not familiar, is the magnitude of the two pieces. So this is going to be 1, and then this is just the magnitude. So it's the real part. And this is very interesting because if I plot it, and I plot it for both positive and negative frequencies, and notice it's symmetric here, is that for low frequencies, I get somewhere around 4, but then as I get down to very higher frequencies, near the sampling rate, near the limit due to the sampling rate, it's nearly going down to 0. So you might imagine this is a low-pass filter because it allows me to have higher frequencies go through and lower frequencies go through and higher frequencies get removed. This is really cool, right? Because it allows me then to start saying, let me selectively look at things. And we can then start looking at a whole range of different transfer functions and approaches for that. The other thing I notice is that if I look at the phase, well, this is going to be real and positive everywhere. So I don't have to, so that's just 1. Sometimes that sign will change and that will change your phase, right? Because, if I take -1, that's actually equal e to the j pi. So that's a phase shift of effectively plus or minus 180 degrees plus or minus pi. But in this case, it's just a constant element. And what's interesting is that this is a constant slope, and that actually means it gives me a constant delay. And so you'll often talk about these as filters that are linear phase or constant delay filters. And these are very, very useful properties in a number of physical phenomena where I want to make sure that all the frequencies that are coming together all have the same delay, and therefore I can aggregate things together. But this gives me a very powerful approach to look at frequency response of any sort of linear system. I used an FIR system here. There's ways to generalize this, but it begins to give you a sense of how you start talking about frequency response, particularly in discrete type systems.